Before Itaipu existed, the Paraná River ran free through one of South America's most strategic regions. But to raise one of the largest hydroelectric plants on the planet, engineers had to do something that seemed impossible. Carve a path through rock, hold back the water with temporary barriers, and force an entire stretch of river to flow somewhere else. Welcome to Invisible Structures. Today, the story begins before the dam, before the turbines, and before the lake. It begins with a country turning on more lights, powering more machines, and needing energy on a scale the old systems could no longer support. In the cities, buildings rose. In the factories, engines ran non-stop. In homes, refrigerators, showers, radios, and televisions stopped being luxuries and became part of everyday life. Every new power pole, every new neighborhood, and every transmission line announced the same quiet pressure. Brazil needed a source that could fuel its growth for decades. And when a country looks to its rivers for energy, it is not looking for water alone. It looks for drop, volume, solid rock, room for giant machines, and a location capable of connecting production to consumption. On the map, the Paraná River appeared as raw potential. On the border between Brazil and Paraguay, it carried enough force to become electricity, but that force would not come for free. To turn current into energy, they would have to build a wall of concrete, install turbines larger than many houses, and create a reservoir where there had once been riverbanks, trees, and rapids. But there was one obvious obstacle. The dam had to rise exactly where the river flowed. So Itaipu's first great question was not how to generate energy. It was how to build inside the path of a liquid giant. And this is where the scale of the project changes, because Itaipu did not begin only as a power plant. It began as an attempt to persuade nature itself to make room for engineering. If you want to understand how a river of this size was diverted and transformed into one of the most impressive energy machines in the world, stay with Invisible Structures and subscribe to the channel. Because now we are going to the exact point where the Paraná River revealed why it was powerful enough to sustain this project. On a map, the Paraná River may look like nothing more than a blue line dividing territories. Up close, it is something else entirely. It is a mass in motion, wide, heavy, and loud, cutting through ancient rock and carrying a force no photograph can fully capture. For a hydroelectric plant to rise there, finding water was not enough. Engineers had to find a place where geography itself worked in their favor. The border between Brazil and Paraguay had that rare ingredient. There, the Paraná River was not just a natural division between two countries, it was a shared force, too large to be imagined from only one shore. The future plant would be binational, with Brazil and Paraguay joined by the same project, the same water, and a structure that would have to operate as one machine. The river carried enough volume to feed giant turbines, but it also passed through a region where the terrain allowed engineers to imagine something almost absurd, turning a natural current into a controlled system capable of producing energy day and night. But a plant of this size is not born because someone looks at a river and decides to pour concrete along its banks. Before the first great machine arrived, there were measurements, maps, soil studies, drilling surveys, and calculations. Engineers had to understand where the rock was firm, where the water could be dammed, where the structures would withstand pressure, and how enormous equipment could be brought into an area that was still far more wilderness than construction site. The chosen point brought together force, strategic position, and room for a colossal transformation. But the same water that promised energy also created the project's greatest problem. The river could not simply be switched off. It would not stop and wait for trucks, cranes, workers, and tons of concrete. The current would keep advancing, pushing, and invading any attempt to build in its path. It was like trying to rebuild a highway while thousands of cars kept speeding through it. Only in this case, the highway was made of water, weight, and pressure. To raise Itaipu, engineers first had to overcome the environment where it would be built. Every bank, every stone, and every meter of current was part of an enormous puzzle. And that was when the project stopped being merely large and started to look impossible. To build the dam in the original riverbed, they would have to create a temporary path for the Parana. Not a simple trench, not a small detour, but a passage capable of receiving the force of one of South America's most important rivers. This is where Itaipu's story gains its most impressive scene. Before raising the concrete wall, engineers had to carve space into the rock and persuade the river to flow somewhere else. And if you enjoy discovering the hidden engineering behind works that seem impossible, leave a like, because from here on, construction begins to face the Paraná River head-on. To change the course of the Paraná River, Itaipu did not begin by pouring concrete into the water. It began by attacking the stone. Before there was a dam, a powerhouse, or a reservoir, workers had to open a side corridor along the riverbank, large enough to receive a current that had no intention of obeying. Imagine excavating a channel not to drain rainwater and not to irrigate a field, but to temporarily carry one of the most powerful rivers in South America. Machines moved in and out of the site as if the riverbank had become an open-pit mine. Trucks hauled broken rock. Excavators bit into the ground, layer by layer. Drills opened holes for explosives. Each blast tore away another piece of the path the Paraná would have to take. The river would not be diverted gently. It would be pushed by calculation, explosion, and containment. To do that, the project needed cofferdams, temporary barriers built to hold back the water while workers prepared the new route. They worked like temporary walls against a permanent force. On one side, the river pressed in. On the other, men and machines tried to buy time. The scene must have seemed absurd. While the current continued along its natural course, a massive opening was taking shape in the rock beside it. It was not the plant yet. It was the space the plant needed in order to exist. An artificial path, carved with precision, where solid stone, dust, mud, and forest had once stood. With each advance, the construction site faced two enemies. The first was the rock, hard and heavy. The second was the water, always ready to occupy any breach. If a containment wall failed, the current could flood work areas, drag away equipment, and put lives at risk. That is why nothing could depend on improvisation. Diverting the river was like performing surgery on a patient who never stopped moving. When the channel was ready, the decisive moment arrived. Opening the passage. The barriers protecting the new path had to be broken, and the water would finally have the chance to leave its original bed and follow a route created by human hands. It was the instant when the project stopped looking like a technical drawing and became a spectacle of brute force. The blast opened the access, and the Paraná began to run through the diversion channel. The water that once occupied the space where the main dam would be built now followed another route. The impossible happened not because the river grew weaker, but because engineering created an alternative large enough for it to accept. Only after that could part of the original riverbed be dried. Where moving water had once been, exposed ground appeared, ready to receive foundations, concrete, structures, and machines. It was as if the project had opened a window in the bottom of the river. This was Itaipu's true physical beginning: shattered rock, diverted water, drying mud, and a gigantic river forced through a path that was not its own. But beating the Paraná for a few meters did not mean the hardest part was over. Now came another challenge: building a wall capable of resisting the pressure of billions of tons of water. And that wall could not be built just any way. In a project of this size, even concrete could become the enemy. When poured in gigantic volumes, it heats up inside, creates stress, and can crack before it ever fulfills its purpose. So Itaipu had to solve another problem, invisible to anyone looking at the finished dam: how to turn concrete into a stable, cool, and resistant structure. If this hidden engineering behind a diverted river makes you see great works differently, subscribe to Invisible Structures, because the most surprising part was still ahead: the dam that had to be cooled so it would not destroy itself. With the Paraná River running through the diversion channel, the construction site finally gained access to the space where there had once been only water. The exposed riverbed became a gigantic work platform. There, Itaipu would begin to rise, not as an ordinary wall, but as a structure built to hold back pressure almost beyond imagination. From a distance, concrete looks like nothing more than a gray mixture that hardens and turns to stone. But in a dam of this size, it could become a problem. In small volumes, the heat of curing barely draws attention. In gigantic volumes, that heat becomes trapped inside the mass. If the outside cools faster than the center, stress appears. And from that stress, cracks can form. For a project like Itaipu, a fissure was not just an ugly mark on the surface. It was a structural risk. The dam had to withstand the weight of the water, the vibration of the machines, temperature changes, and time itself. That is why building with concrete there did not simply mean pouring material, it meant controlling every stage. The concrete had to arrive at the right temperature, be poured at the right pace, and cool in the right way. Production plants, laboratories, chilled water, ice, and constant measurements all came into play. The logic was easy to understand, but difficult to execute. Keep the concrete from destroying itself from within before becoming the wall that would hold back the river. The dam grew in blocks. Layer after layer, each section had to gain strength before receiving the next. Nothing could be rushed without consequences. It was like assembling an artificial mountain with the precision of a clock. On the outside, it looked like brute force. On the inside, it was thermal control, calculation, and patience. And the scale helps explain why all of this was so delicate. Itaipu used about 12.7 million cubic meters of concrete. The dam stretches almost 8 kilometers and reaches a maximum height of 196 meters. It was not a wall crossing a river. It was a chain of connected structures built to turn stored water into controlled energy. As the concrete rose, the plant also prepared its inner spaces: galleries, technical passages, floodgates, inspection areas, and the future powerhouse. That is where the equipment would sit, giving meaning to all that concrete mass. Because the dam, by itself, did not generate energy, it created the conditions for the water to gain height, pressure, and direction. Little by little, the construction site stopped looking like an open excavation and began to take on Itaipu's final form. The river still followed the diversion, but that solution was temporary. At some point, the Paraná would have to return and press against the main structure. And then one of the most tense stages of the project would arrive, closing the temporary path, letting the reservoir rise, and discovering in practice whether that cooled wall was ready to turn the river's force into electricity. After about 10 years of carving rock, diverting water, and raising concrete, Itaipu reached the moment when the project had to stop looking like a construction site and start behaving like a power plant. The temporary channel that had carried the Paraná River during construction was no longer the main path of the story. It had done its job. Now the water had to return and press against the structure prepared for it. Closing that temporary path was not just a matter of setting a barrier and waiting. It meant allowing the river to begin rising, meter by meter, forming a reservoir where riverbanks, rapids, vegetation, and old landmarks had once existed. The water advanced slowly to anyone watching from far away, but on an engineering scale, it was enormous. Each hour meant more weight against the dam, more pressure on the structures, and more responsibility on everything that had been calculated. Lake Itaipu was born from that tense weight. As the level rose, the project began to reveal its true purpose. The dam had not been built to stop the river forever. It existed to organize the force of the water. What had once been a free current now gained height, direction, and control. And this is where energy begins to be born. The water stored in the reservoir enters through massive intakes, descends through enormous conduits, and reaches the turbines with brutal force. Inside, the pressure turns gigantic parts connected to generators. The movement of water becomes mechanical motion. Mechanical motion becomes electricity. And electricity travels through transmission lines to cities, industries, homes, and machines that may never imagine the journey that energy has taken. Itaipu's turbines are not hidden details inside some ordinary room. They are colossal machines designed to work with constant flow, vibration, weight, and precision. Each generating unit turns part of the Paraná's force into electric power. Together, they make the plant one of the largest producers of hydroelectric energy in the world, with 20 generating units and 14,000 megawatts of installed capacity. But a plant this size also needs to handle excess. When there is too much water, one of Itaipu's most impressive images comes into play: the spillway. It works like a monumental safety valve. Instead of letting the reservoir rise beyond control, gates release immense volumes of water, creating violent drops, mist, noise, and a clear sense that nature remains powerful, even inside a planned structure. What is most striking is that, once finished, Itaipu hides much of its complexity. From a distance, people see concrete, water, and transmission lines. But inside, there is a technical city: control rooms, galleries, sensors, inspection systems, gates, cables, tunnels, and teams monitoring signals almost no one sees. The visible part impresses through size. The invisible part keeps everything working. In the end, Itaipu was not just a project that placed a dam across a river. It was a complete transformation of the landscape. A stretch of the Parana changed its behavior. A lake appeared. 2 riverbanks, 2 countries, and thousands of workers became linked by one structure. And a force that once ran free began feeding entire electrical grids. Maybe that is the great image of Itaipu. A project that began by trying to carve out space inside a river and ended by creating a machine capable of turning water into light. If this video made you look at a hydroelectric plant differently, subscribe to Invisible Structures and comment on what surprised you most about this story. And take a moment to say whether your city is powered by another hydroelectric plant or by some other form of energy generation, because behind every glowing outlet, there may be a gigantic structure you never see, still working in silence.